Now, before we get into maybe the nitty-gritty of these infinite series and infinite sequences, perhaps maybe the more important question is, which Toy Story movie was your favorite? Would you admit it? Did you watch the Toy Story movies? How about Toy Story 1? Do you remember that one? Who was that mean, evil guy? Sid. Actually, my kids were actually a little bit scared of him. I mean, I don't care if you tell them, but that was quite a while ago. He was kind of a scary dude, what he was doing to those toys. So I saw some of you say Toy Story 1. There's, sometimes you got to go back to the original, right? That's always the best. 2. This one people seem to have trouble remembering. Sorry if you didn't watch them. You're feeling a little bit left out. The big chicken guy, the toy store owner guy.
Which one was the one with like the trash truck?
That's 3.
Oh, that's the good one. That's Which one was the one that was in the daycare?
Now, Toy Story 3 was Sunnyside Daycare.
Oh, I like that.
Sunnyside Daycare. So yes, it's all right to admit that you cried during Toy Story 3. We had some tears in our house also. It was a good one, right? And of course, that bear got what he deserved. A forever ride on the trash truck. He was mean, though. I mean, come on.
I think he was misunderstood.
When he let them continue down the conveyor belt. Yes, he had some bad things happen to him, and then Toy Story 4. Some of you remember that was the one with Bo Peep, right? Is that the name? That was kind of different. It's hard to make a 4th one good, but I think they did a good job. I sometimes they get worse, but they actually did get better.
Spud said, I forget the girl's name, she will be okay. I'm like, oh, no.
Yeah, I'll tell you, the writers of those movies is what really kind of almost, I guess I look at that stuff, but whoever wrote that stuff, man, they were really creative and how they connected all the different movies, so pretty neat. All right, so infinity. Now, it does have to do more with numbers than a toy, but the strange thing about infinity, just kind of to share, it's hard to honestly think about as a human, at least in these bodies where we have beginning and end. And so now we're going to talk about something that sort of has no end. And there are times where it's kind of like, I'm having trouble understanding that, like mathematically, even myself, kind of like, how can I think about something that goes on forever? And that's actually what we're trying to get you to do with numbers. Okay, now before you say, well, isn't the answer then just infinity? Like what if I asked you, what is the infinite number? What is the, so to speak, last number? Is the answer always infinity? Well, that's why we're together talking for a few minutes. And what if I try to add these numbers up? What if I try to add an infinite amount of numbers? Isn't that answer going to be infinity? Well, not necessarily. And again, that's why we're together. So it's kind of strange. Like there's going to be a point in today's lesson where you're like, oh my gosh, wow, actually we have an infinite amount of numbers, but the answer is not infinity. What do I mean, the answer? Let's kind of look at these sequences a little bit more closely. Now, remember, a sequence is just like a list of numbers. So we have the list of numbers 2, 4, 6, 8. It's kind of a neat list. But if I would ask you to think about the, so to speak, last number, in other words, the infinite term. Now, again, when I say the infinite term, I just mean like what's going to happen is the numbers continue in this sequence. Well, in this case, they would not. In this case, the infinite number itself would be infinity, because as I hope you see, each of these numbers just keeps growing and growing. So, of course, the next number is going to grow, the next number, and if for some reason I could list an infinite amount of numbers, my last term would just continue to be a larger number also. So that means that these numbers are divergent. They're divergent because, well, because they're not doing anything other than getting bigger and bigger. And we actually say that they're divergent to infinity. Now, again, sometimes kids will say, well, wait, what do you mean by that? And again, I just mean that as the numbers continue to be listed on forever, that the infinite term itself will be infinitely large. And in some ways, I haven't said too much yet because we are unable to get to that last number because it's divergent. It never goes to a certain value. Look at these numbers here. Now, you should feel like that they are changing differently. It's not like I'm just adding 2. In fact, you should say that you're multiplying by -2, right? You're multiplying by -2. So, okay, I could multiply the next number and then the next number. And wait, that means that the next number is going to be like positive. And then wait, the next number is going to be really negative. And then the next one's going to be, and then the next. So the numbers keep like bouncing back and forth between a positive and a negative number. And of course, each time they themselves keep getting bigger. Well, we have another example of something that's divergent. And again, to be divergent just means that the numbers are not approaching any value. Now, we could be a little more specific here because the numbers keep bouncing back and forth between positive and negative, that we could say it's divergent to plus or minus infinity. It's just a little more specific because we have, of course, positive and negative numbers. Now, so far, it seems like the answer just seems to be infinity every time until we get to this last sequence. Now, how hard have you studied this one? First of all, do you realize how we're getting to the next, and the next? What are we multiplying by? 1/3. Well, I bet you could tell me the next number. It would just be 127 times 1/3. And then I bet you could tell me the next number. And then the next one. Now, wait a minute. If you keep multiplying the denominator by 3, what's going to happen to these denominators? And if I keep having 1 over that denominator, what's going to happen to my overall value? What number is, so to speak, the last term, is the infinite term? 1 divided by a really big number. And then 1 divided by like another really big number. Yeah, and if you have 1 over infinity, like what number are you kind of like getting closer to? If you take the number 1 and you divide it by a large value, 0. Now, here's kind of the strange idea. You never get to 0, do you? You always have 1 divided by something, but it's getting really darn close. It keeps getting closer and closer to nothing, to 0. And that idea that we're trying to understand means that this sequence is convergent. It's convergent, meaning it actually does approach something. And that something, as was spoken by some of your classmates, is 0. 0. I'm going to spell it out just for emphasis. 0. Having trouble with that Z. Now, before we go any further, just kind of let this sink in. If I have an infinite amount of numbers on the board, it could be that my last number actually is something, is like a value. These are not values. These just go on forever, but this is actually a value. Okay? And yet I still never get there. That's what means that I'm just converging on it. I'm getting closer to it. Ready to keep talking about infinity? What if I try to do a series? Now, I was impressed by how you guys picked up on the language from the snow day videos, that we have a sequence, in other words, just a list, but then we have a series, which sometimes we put the word sum in front of it, which is actually kind of redundant, but it is often what we do because that's what a series is. It's actually adding the numbers. So, well, think about it. If I add all those numbers, 2, 4, 6, 8, and then the next one and the next one, if I add an infinite amount of numbers, then the sum also appears to be doing the same thing, doesn't it? I just keep adding a bigger number and a bigger number. That's because this is arithmetic. And because it's arithmetic, as we've said a few times, the numbers just keep growing and growing. So an arithmetic series is going to do the same thing. In other words, if I just add all these numbers, I'm not going to be getting much done except growing to be itself a large infinite value.
How do you like look at a sequence and determine whether it's arithmetic?
That's a good question. Maybe we should have said that out loud, but when you look at 2, 4, 6, 8, you should say that they are changing or growing by the same difference. We call it the common difference. The letter D was used in the video. So when I look at this, I see the number 2. And because it grows by the number 2, it's arithmetic. Again, when I say grows, I mean like you're adding 2, called the common difference. Actually, when we go down to this one, as we already said, it looks like each number is being multiplied by -2. Now, since it's being multiplied, that means it's geometric. Again, since it's being multiplied, it's a geometric sequence. But what if I would add all these multiplied numbers? Okay, now before we give the answer, r equals -2 is going to be an important conclusion. We just want to keep that in our back pocket. And as you'll find out, it's actually the absolute value of r that is most important. And so I'm going to put these absolute value symbols here, but we still kind of see this number 2. But again, if I'm adding negative, then I'm adding positive, and then I'm adding negative, and then positive. Now it's interesting, if I'm adding these positive negative numbers, it seems like they might kind of like balance each other out a little bit. But really, when I add the positive number, now my sum is positive, and then now I'm going to take away 8, so now I'm back to negative, and then I'm going to add positive. It keeps bouncing back and forth as you add these numbers. You might think that it would bounce back and forth to 0, but it's always either above 0 or less than 0 as you add these numbers. And so if I do that out to infinity, I'm just still going to be bouncing back and forth between positive and negative. So we could say that the sum is still going to be infinite. And to say positive or negative just means that I might have a negative answer or a positive answer. Now again, everything looks like the answer is just infinity until we get down to this last one, where we have maybe the most interesting part of today's lesson. What happens if you add an infinite amount of those fractions? What happens if you add an infinite amount of those fractions? Well, whenever I wheel this big thing over here, you know we're going to do something on the calculator. That something is actually to just observe what happens when you add the first couple fractions. Now you can observe with me, or you can try it yourself. Make sure you realize what I'm doing. Like I'm literally adding, I guess, 4 fractions? Okay, now that's not an infinite amount of fractions, but if I add 4 of the fractions, I get this value. Now, again, I'm supposed to be adding an infinite amount, so maybe I could at least add 1 more. Did you do the math? Next time you multiply by 1/3, you're going to get 1 over 81. 27 times 3 is 80. So I'm going to add the next fraction. Okay. Now I'm supposed to be adding an infinite amount of fractions, so geez, I maybe should at least add 1 more. 81 times 3. Did anybody do that like off to the side? I think it's 243. Yes? Okay, 243. Now, what a student like you should be doing here is making some educated observations. And an educated observation can turn into an educated guess, and an educated guess can actually turn into an educated answer. You say, what answer? Well, we're trying to figure out what happens when you add these numbers up. It looks like, well, let's add the next fraction. Now, I know this one, it's 729, but before I hit enter, just think about what I'm about to do here. 1 over 729. How big is 1 over 729? Not very, right? It's like I'm adding that. Okay, I'm adding like 1 729ths. So what does that do to my sum? Are you starting to see where this series is converging? 148, 149, 149.9.
To 1.
It certainly seems to be, and it is. It's amazing. If you add an infinite amount of these fractions, you're never going to surpass 1.5. In fact, you're only going to get closer and closer to 1.5, which is why we say that for this geometric series, that, now remember, when I say series, that means sum. And so that means I'm adding up an infinite amount of numbers. And yet, when I add up an infinite amount of numbers, I'm never going to surpass 1.5. Just let that sink in a second. An infinite amount of numbers are listed. You're adding them all up, and you never will get any further than 1.5. Now, that's because we have a special R value for this problem. Technically, the absolute value, but really the R value is, well, has been 1/3.
Does any fraction converge on 1.5, or is it just?
It's not just the 1/3, but as you'll find out, it's any R value less than 1. Any R value less than 1. Okay, and that's what's kind of special here. We have an R value greater than 1. And if you guys do a little thinking about numbers, obviously if something's bigger than 1, it's just going to keep growing. But interesting, if I multiply by something less than 1, I'm actually allowing it to shrink, which is why this converges to 1.5. Let's make some conclusions here. Now, the conclusions are very similar to what we already did, but I called it facts, and it matches with the screen here. So, some facts. First of all, if you add up an infinite amount of arithmetic numbers, as we've kind of said now a few times, it's infinity. If you add up an infinite amount of arithmetic numbers, again, the answer you might put in this box here might be something like infinity, or you can even put that whole phrase there. Now, that's like an always, okay? It's an always. In fact, it's always true that if you add up an infinite amount of geometric numbers where R is greater than 1, that also will be infinity. And again, you probably put that in this box. If you have an infinite amount of geometric numbers where R is greater than 1, your answers, your sum is not going to come to any value. It's going to also add up forever to infinity. Now, it's this last one that is kind of the big deal today. And that is if you have a bunch of geometric numbers where R is less than 1. Okay, now if you have a bunch of geometric numbers where R is less than 1, there's actually a little formula. There's a little formula. Now the formula is a formula for the series. Okay, when you see that letter S, that stands for series. Some people say sum. It's fine. But the series will be the first number simply divided by 1 minus that ratio. It's actually the simplest formula of this chapter, and it's so interesting because it works for an infinite problem. And all you need is the first term, and then you'll divide it by 1 minus the ratio, which I'm going to show you for this problem. It's kind of interesting. You still have a little bit of space. I actually want to do it for this problem. Now, when you write the notation S, it probably should have a subscript of infinity. Quite honestly, I probably should have put a subscript on this formula. You want to put it there. S sub infinity just stands for this infinite series. So I'm adding an infinite amount of numbers. Now check this out, because it's almost so simple, I just don't want you to miss it. It's the first term, which happens to be the number 1. So the first term, which happens to be the number 1, divided by 1 minus the ratio. Remember, the ratio is this 1/3 number. It's always, no, well, that you plug into the formula? No, you would plug in the actual R value. Yeah, you could be plugging in a negative number, technically. But when it comes to thinking about the comparison of the number, we always compare it absolutely with the number 1. Now, I guess if you already put this in a calculator, the secret's out, but it's kind of interesting without a calculator because 1/2 is kind of like 1 divided by 2/3, which is the same as 1 times the reciprocal. 1 times the reciprocal of 2/3 is 3/2, otherwise known as 1.5. And so it works. This simple little formula works. Okay? Little sort of be careful. Sometimes kids use this formula for some reason for like every problem from now to the end of the chapter. Don't be that kid. This formula only works for an infinite geometric series where r is less than 1. Think about the assignment that you turned in. There were plenty of problems in there that were not infinite and you used other formulas. Now, to help you kind of process this, we're going to make another chart, but this is a little more of some examples, like actually doing some math problems. And I don't know if I would draw all the lines. Why don't you draw the lines as you go? Make 3 columns. In fact, what I'm going to do in the middle column is I'm going to put the example. And then, as you'll see, we're going to do some comparing, which is the other 2 columns. So here's a sequence, 9, 6, 4, 8/3, ... And I like this. This will be good for you guys to see these 2 comparisons, even if you're kind of like, I'm not sure if I get what you're saying. It usually makes more sense with some problems here. So what if I asked you to add an infinite amount of these numbers? In other words, the infinite series. So what if I asked you to add an infinite amount? Well, the first thing you'd have to do is you'd have to think about what kind of series or what kind of sequence we have. Okay, as Owen kind of said, how do you know which kind you have? Well, you can look at the numbers. You should quickly say that they're not being added or subtracted by the same amount. It does look like, though, that they could be geometric. How do you know for sure? You divide. You could take 6 divided by 9. You could take 4 divided by 6, just like we taught you a couple lessons ago. And if you do some simple dividing, you quickly arrive at a common ratio of 2/3. That's important, though, that you realize that the ratio is 2/3, because that means that this thing is geometric. And since it's geometric and r is less than 1, I'm able to use my formula. I'm able to use my new infinite formula. So how does this work? Well, it looks like I just need the first term. That's the thing that's so interesting about this. I just need the first term, which happens to be 9, minus, 1 minus then that common ratio of 2/3. Now, you'll have a calculator if you want. I do like to kind of show you guys that there's some interesting math in some of these problems, like just 1 minus 2/3 is 1/3. And here we have another example of being able to think about multiplying by the reciprocal. 9 divided by 1/3 is just the same as 9 times 3. Again, somewhat amazing. If I have an infinite amount of these numbers, I'm going to converge on the number 27, never any greater. Now, to help you kind of compare a little bit, what if I just have 10 of these numbers? What if I just have 10? Now, that would mean that I'm finding the 10th partial sum, S sub 10. It would also mean that I have to pull a formula out of the formula bag that you've been working with the last few days. Okay, I'll help you with the formula, but it's that somewhat larger one where you take the first term and then you subtract it with the first term times a base to an exponent, and then it's all over 1 minus r, which is still 1 minus 2/3. I'm kind of giving you a skeleton of that formula because I just want you to realize how similar it is to our infinite formula. In fact, the only thing that's different is this minus 9 times the base maybe I should say the ratio, to the nth power. The only thing that's really different is that subtraction part. Okay, it's a calculator problem. Some of you asked me for some help with the calculator. The main help that I give is that you do have to be heavy on the parentheses. I hope that you've been doing this correctly, especially in the assignment that you turned in. I hope that the answer that you get here makes sense when you compare it to our infinite answer. Okay, are you getting 26 and about a half? Okay, because think about it. I'm only adding 10 numbers, but geez, with just 10 numbers, I almost get the whole way up to my infinite answer. I almost get the whole way up to 27. In fact, the remaining infinite numbers from 11, 12, all the way to infinity, the remaining infinite numbers will only get me a measly half worth of value, because that half is what's going to get me up to 27. Okay, so you get most of your value in the first numbers. Okay, two different. Good.
I'm sorry. Is that the same formula for a geometric series?
Yes, that is the geometric formula. I'm glad that you're processing that. That is the geometric series formula. This is the geometric infinite series formula. So it's kind of like a little derivation of it.
So you only use that when you're trying to find the next.
Yeah, the infinite sum. As you said, the max number. That's fine. Let's compare another one. I think you'll get the idea here, but I'm going to get a little fancy here with this sequence. 3, 0.3, 0.03, 0.003, ... 3, 0.3, 0.03, 0.003. Now, I know this chapter brings different emotions to kids. Some kids, they really kind of just like this number theory stuff. Some people, it makes them a little nervous because, like, I don't know if I'm going to get this right. Like, I'm going to look at it wrong. Remember, when you look at these numbers, you want to try to figure out how they're changing. It's pretty clear that we're not adding or subtracting from number to number. Maybe we're dividing. Maybe, because of the way the decimal is changing, you can just get right to it and you can say that you're multiplying by. Now, if we're just moving the decimal one place every time, that would be the same thing as multiplying by a tenth. Okay, now multiplying by a tenth is also the same as dividing by 10, which you can also find if you just divide these numbers on your calculator. But the bottom line is every time we're moving the decimal one place. Hey, that's another ratio that's less than 1, which once again means that this thing's geometric and it's also converging. Since it's converging, we're able to go over here and pop out another answer. Okay, what kind of answer are we going to pop out? The infinite series, which requires the first term over 1 minus that ratio. It's a really simple formula. Just understand, please, that it is providing you with the infinite series. Now, 1 minus a tenth is 9/10. If you want to do a little bit of number crunching without your calculator, but it's fine if you type this in. Again, it's totally fine. I actually kind of want you to see the number, and maybe you're not surprised by what you're seeing, because we're really just adding a repeated 3, a repeated decimal of 3, or 0.33. So what happens if I go over here and add 10 of them? What if I go over here and add 10 of them? Well, I'm going to do something that kind of breaks Mr. Naylor's rules, where I say to not use brute force. Now, when I say brute force, I mean like completely disregarding formulas for this whole chapter, because you'll have a lot of trouble. But sometimes brute force or just thinking is easier. Like, I want you to think with me for a second. I'm really just adding 10 of these numbers together. Wait, 3 plus 0.3 plus 0.03? 3 plus 0.3 plus 0.03 plus, how many 3's am I going to line up here, including the first one? 10. I got 4, 5, 6, 7, 8, 9. The point behind this problem is the devil in the detail. This is an infinite amount of repeated 3's. Is different from 9 repeated 3's, a total of 10, counting the first one. Do we understand that this number is a little bigger? Okay. This number is technically 3 1/3. This is not technically 3 1/3. This is a tad bit less than 3 1/3. Okay. If you're like, so what would I do on a test? If you're like, that's the kind of question on your mind, you have to understand that you have to represent these two answers differently. Right now, I'm just trying to get you to think. Okay. The difference between infinity and then a partial sum. Here's a sequence. 2, 4, 8, 16. 2, 4, 8, 16. Let's figure out what kind of sequence it is. How are the numbers changing? A little bit of observation. You should feel like that every time we're multiplying by 2. Now, if you notice that you're multiplying by 2, you just came up with what's called the common ratio. Uh-oh, that common ratio is greater than 1. Wait a minute, what does that mean for an infinite amount of those numbers? Well, it means that there's no sum. The best we can do is kind of state that by saying infinity, but you got to understand when you write infinity, you're really saying that that sum is not defined. We don't write undefined because we can describe it a little bit more with the infinity symbol. But if I add up an infinite amount of these numbers, nothing happening. Okay? It fits into this category. But that doesn't mean I can't add 10 of them. Uh-oh, how do you add 10 of them? Okay, you got to go back to a formula. It's the geometric series formula. It requires you to have the first term minus the first term times the common ratio to the exponent all over 1 minus that ratio. There's a lot of 2's in this formula. Please understand that one of those or two of those 2's represent the first term, and then 2 of those 2's represent the ratio. Okay, if you're kind of motivated to do that on your calculator, that's fine. Make sure that you can do it. And the answer should kind of make sense. You know, this pops out to be 2046. Yeah, you know, if I'm going to add up 10 of these numbers and put a plus sign between them, eventually we're going to be adding up some numbers in the hundreds and high hundreds. So if I'm adding up 10 numbers in the high hundreds, eventually I'll get to 2,000. How you guys doing? We have one more that we're going to do, but as I kind of started the lesson, I know infinity can be a little strange. Okay, I don't want you to leave the lesson thinking that the answer is always infinity, and I don't want you to leave the lesson thinking that the answer is always this formula, because of course it depends on the type of sequence we have. So here, 9630, sounds like somebody's phone number, 9630 ... Just kind of wondering what you're thinking. If you're not totally spent here, what are you thinking? Good. So it has a common difference, which would be actually good. They're allowed to be negative. Now, when Reba says common difference, I can sense it's implied that that's arithmetic. I mean, you don't need to write that if you don't want to, but it's arithmetic. Oh, what if I add an infinite amount of arithmetic numbers? Honestly, it doesn't matter what the numbers are. If they're arithmetic, it's not going to add to anything. Now, We can be a little more specific here if we want to be, and we can say, yeah, they're going to add to negative infinity, because obviously they're going to get negative soon. If you just wrote infinity, I would give you credit, but we can use negative infinity to be a little more descriptive. And one last time, we come over here to the partial sum formula, right? That I don't have memorized yet. Well, it's all right if you don't have it memorized yet, but you recognize it. It's n divided by 2. So it's 10 divided by 2. N divided by 2. And then, the first number plus the 10th number. The 10th number. Well, we'd have to do a little figuring, right? Now, you probably did this on the assignment more than once, but the 10th number actually technically requires another formula where you could solve for a sub 10. I'm just going to tell you it's negative 18, but you have to understand that you would have had to find that number, which I hope you did a time or two on the assignment. If I add up 10 of these numbers, a lot of them being negative, yeah, it kind of makes sense that I'll get to negative 45. Whoa. Homework helper, just A through E. Just A through E. Something different tomorrow. Something different tomorrow.